Good afternoon. Good afternoon. So I'll continue from where we left off yesterday regarding the example of how we do our analysis of time complexity. And what I'll actually do is produce, there are a couple of steps. I will get as far as the analysis step where we'll continue that process. Yesterday, when we got to a point where we wrote down what the time complexity was, but it looked like it was going to be in terms of itself. And what I'll do is finish that example and get it to a point where you won't actually see the final solution, but we'll get it to a point where we can make some estimates about it, given what you know. There's going to be a whole topic to come on how we actually get that final step done, but today's not the day for that. I just want you to be aware of how you apply the rules and to get comfortable. So I may even run a separate example if I have the right amount of time. And then towards the end of the week, by the end of the lecture today and then the end of the week, there was a particular bit of revision that I had intended. I noticed that I had it as item 2. On Monday, I accidentally skipped it, went to item 3 in our syllabus. So it will come in here. It doesn't affect the tutorial structure of that tutorial for the whole week. So it's the same content, just slightly out of order, because this is something you covered in year 1, I hope, but we'll see how that works. So the example we had yesterday, let's just write back that code so we can look at what we're analyzing. That's what we had yesterday, right? And what I said to you is, when we're analyzing this time complexity, what we're doing is counting operations. And the important thing is to recognize that you're really simulating the execution of the code when you're doing this. So when we said the time, so that's the algorithm. Now we're looking at what happens when you execute mul1 on some argument p. Oh wait, you have it in your notes. I don't have it on the board. Let me just put back the basic up so you can see what we're counting. That's why I write it down, because we need to be able to see what is being counted. So it said plus, minus, left shift, right shift. Was there even? And equal. I think. Were there any more? That was it from yesterday, yes? Okay, and we had agreed after a little bit of discussion that, remember the second step was decide what the size of input is. And I pointed out to you, and you all agreed, that it's the value of Q. That the value of P was basically irrelevant to the amount of time it's going to need to run. And what really mattered was what the value of Q was. So we got as far as then saying, okay, so now suppose I put an arbitrary value n in for Q. In other words, suppose my size of input is this unspecified quantity called that we'll just refer to as n. It's fixed, it doesn't change per se, as in it is the size of the input on a given run. But we don't know what it is, so we need to express our answer in terms of n. That's the important thing. So we get a function in n by the time we're finished. So how we do that is simulate what would happen if we were to run the algorithm with an input of size n. So in this case, since the size of input is just a value of Q, that means simulate what would happen if we were to run the algorithm with an input of size n. And what we said yesterday was, okay, when you run mul1, what that really does is call or invoke this if. You call this function, you set up the call. We're not charging time for that. We're going to count that as if it doesn't count for anything. Instead, what we're going to do is immediately jump to the body of the code and say, okay, now let's assess what the cost of executing the body of the code is. So what we say is that this is really equivalent to asking, what is the time for evaluating this if expression? And what we'll see is, so I'll write it out as if, no, I'll write it like this. No, sorry. I'm going to write it explicitly the way it looks. So it's code. So it looks like this is the actual code that you see. We know that Q is actually had to by the n. That is the equivalent code that we're evaluating, bearing in mind that the value of Q in this context is bound to whatever n is. So now, this is really the same thing as what? Well, when you execute an if, the rules for executing the if is you must evaluate the predicate, no matter what. That's the first thing you do. Execute the predicate. Then, depending on the result, you either evaluate the consequent or the alternative, but not both. Remember, we're counting operations here. So we have to take into account all the possibilities. So what we're going to say is, if the input, which in this case, well, what is Q? Q is whatever that n is. So whether Q is 0 or not really depends on what n is. And that's why we have to have this brace to indicate that we have, it's an option, it's a conditional value. Yes? Rule for if? Yeah. How do you evaluate an if? Well, what I'm asking you. When you execute an if, when you write an if statement, what do you expect to have? Yeah, isn't that what you're supposed to? I didn't think I said anything new. That's why I'm asking you. You never write an if statement before? Terminology. Oh, the words predicate, consequent, alternative. That's what you mean. Okay. Sorry? Yes. So, okay. I don't know how to call it then. First part. Yeah, that's fine. Okay, that's specific. That the expression that's supposed to give it true or false in the if statement, that's called the predicate. The part that comes after the then, if the predicate is true, the piece is supposed to execute. That part is called the consequent. And in the case it is false, the piece that comes after the else, that part is called the alternative. Okay? So those are the three pieces of an if statement. That's what I was referring to. That answer your question? Yes. Okay. Okay, so yeah, so pressing on. So we have to execute this if according to the rules. That's what it means to simulate the execution. So remember, we're counting anytime any of these operations show up, as in not just appear, but actually get executed. So to evaluate this, if I would have had to evaluate this predicate tests equality. So here I am executing one of those basic operations. So to count that, in the case, so now I have two possibilities, either n is 0 or it's not. If n were 0, then I'm going to execute equal. So that's one operation for equal, plus the time to do the return. And this is if n is equal to 0. If n is bigger than 0, as in if it's not 0, then we still had to have done the equal test. That's how we knew it wasn't 0. So we still have to spend that time for that expression, that operation. But now we have to then execute the alternative. Oh, return. Yes? Okay, so now, remember I said yesterday that I should really write out the rules, but I've actually, the rules have already been written out for you in that manual. Did I mention this course manual? I thought I did. Okay, so if you look in the course manual, you'll see the rules set out. You can look at that to see the general description of those rules. I'm trying to demonstrate it by example because I think that's going to be easier to grasp. So if I now evaluate what happens when n equals 0, what I'll see is, okay, what's the time to the return of 0? Now, according to the rules, here's what we do. Look, to evaluate a constant, free. Don't charge for that. So to keywords like return, we don't charge for that either. Reasoning is that a return is simply really copying a value from one location in memory to another. And for the general case, we tend not to count memory movements. There'll be some times when the only thing going on is memory movement, in which case we'll count those or try to. But for in the general case, when we're analyzing our algorithms, we're not too worried about what it takes, how much time it takes to move data between memory locations. You see, in some cases, those might be registers that we're moving in between. In other cases, it might be actual RAM that we're moving between. Those cost different amounts. It's not worth it to get into the details of that because at the end of the day, we're only interested in orders of growth. And so whether you put, if it costs you 10 time steps, or if it costs you 2, or if it costs you 1, The only difference that's going to arise is the constant in your final analysis. And remember, in our orders of growth discussion, we realize that it doesn't matter what kind of constant you put in front of the expression. For example, 10 times n to the fourth is still theta n to the fourth, no matter what that constant is. And so because of that, we don't need to bog ourselves down with getting into worrying about how many actual steps were involved in a particular kind of memory movement. So things like return, don't charge for that. Any kind of special syntax, like we're not charging to evaluate this if and the else. We're only charging time to evaluate the other expressions that come with it. Okay, so those are some of the general rules. So bearing that in mind, this is essentially zero. Don't have any cost to doing a return of a constant. So that gives us that the cost is going to be 1 if n is 0. And now we come down here, what do we see? Well, we're seeing a 1. Let's put back that equal so you can see where it came from. Now, as I evaluate this expression, return p plus mol 1, p, q minus 1, what are some of the operations that you can see will need to be evaluated? I'm going to need to evaluate that plus, that is true. What else? That minus, okay? What you call the multiplication? The call to mol 1, right? Right. So that's our call to the function that I'm trying to analyze. In other words, I'm trying to analyze what is the time for mol 1. And that's what I'm going to invoke in the else clause. So let's capture that. But for this once, I'm going to do it deliberately in the order in which it was actually executed. It's not terribly important because addition is commutative. Doesn't matter what order you add up the addends in, or the summands in, get the same result. So, but since we're simulating this, for your benefit, I'm going to write them in the order in which they would have actually occurred. So which operation occurs first? The what? The subtraction. Why the subtraction? Correct. So think of it this way. If you try to evaluate the plus, you need both operands. But the second operand requires a function call. And in order to do the function call, you need to have subtracted 1. So the very first thing that actually gets done is the subtraction. How much time do I charge for the subtraction? It's 1 because it's one of those basic ops. So I have 1 for the minus plus. Now, what's the time for that recursive call? Well, that's what we're trying to figure out in the first place. So it's like, oh, whoops. Well, we don't let that bother us too much. We just write it down as we see it. So it is the time to do the mol 1 p. And now I'm going to put here, I'm going to put a little notation here to indicate what that value actually is. So that angle bracket is to indicate that the subtraction has already happened. I'm not saying, this one says, this is actual code that says you need to subtract 1 from Q. I'm trying to indicate that I've already subtracted 1 from Q. It is the value that I got that I'm now passing to mol 1. You understand what I'm saying? So I'm just designating that with this angle bracket to indicate that it's done already. It's not another subtraction. That is the result. So Q was n. So when you subtract 1 from it, you get n minus 1. That make sense? That's what I'm designating right there. And of course, after the product, after the mol 1 completes, I still have one more operation that was this plus. So the time for the plus is how much? 1. Because it's a basic op as well. And all of this is if n is greater than 0. Okay, so let's simplify this. So I get 1 if n equals 0. I get 1, 2, 3 plus the thing I'm trying to work out. Otherwise. And that doesn't help me, sorry, it helps me, but it doesn't answer the question that I want quite yet. I want to get a handle on this. So what I'm going to do is, I'm going to abbreviate this. Sorry? Can't hear you. I appreciate that. I don't have any more space anyway, so I got it right here. In fact, I gotta actually, I understand that the cable people can't see much, so I'm gonna actually bring that camera on and just let them see the board and then the back. So, I want to abbreviate this so I don't have to keep writing this out. So let me just call this time complexity, whatever mole 1 takes when you give it n as an argument, we'll just call that T of n. T for time, n for the size of the input. So let that represent, let T of n represent the time complexity of calling mole 1 with some argument p and n as the value of the second argument. So according to what we've derived, what we have is T of n is 1 if n is 0, or 3 plus, now how do I write this as T of something? T of n minus 1. Exactly. So now what do I have here? I have an expression. I mean, I had it even here, but it's more obvious. It's more clear to see. I have here an expression for T of n in terms of itself at a smaller value. See that? There's a name for that kind of function. One is that is inductively defined. Ever heard of that? Sorry? One is inductively defined function. What's another name for it? It's on the board. Or recurrence relation, right? You guys have seen that term before, right? Discrete maths? Maybe somewhere else? If you've done discrete maths, that means this is cakewalk for you to solve. You can solve this in your sleep. That's okay. It's actually on this syllabus. We will talk about how to solve it, but not today. That's next week's topics. But let me help you figure out what this would be for now, just so that we have some closure on this question of what is the time complexity of mole 1. But what we're doing is trying to find a function for that time. I want to now simplify this to look like T of n is something with n, not this if and whatnot. Can I just get a simple expression in terms of n? So this apparent self-reference and conditional situation. That says yes, of course, and we'll deal with the techniques next week. But for now, let me just, you can do this by, you could try and pattern match and guess, and then use a proof by induction to prove that what you guessed was correct. So let's take that approach, because that's not the best approach, but let's take that approach for today. All those techniques I just mentioned, you've seen before. Proof by induction, guessing and spelling, you know all about that. All right, so let's try a thing. What is T of 0? All right, so we need, here, parenthetic comment, need to simplify T of n. We'll cover the technique next week. Today we're just doing our thing. So, observe. What's T of 0? All right. What's T of 1? According to this, 3 plus T of 1 minus 1, 0. But we have T of 0. So then this is 4. What's T of 2? According to this, it's 3 plus T of 1. And T of 1 is 4, so this is 3 plus 4, which is 7. Okay. That tells us what T of 1 and 2 are, but we need T of n in general. Huh. Anybody willing to hazard a guess, or we need some more examples? 3 and minus 1? Test it. 3 ones, 3 minus 1 would have been 2. You sure you want minus 1? 3 and plus 1, right? If you don't believe it, you can try some more examples and see. Eventually, you'll have done a proof by induction to prove that this is actually true in general. And you'll then be able to convince yourself that that's right. So T of n is 3n plus 1 is the final answer that we'll get for the time complexity of this algorithm Mulva. Absolutely. But that is like a good analogy. That's like bringing a jackhammer to push a thumbtack into a cork board. Yeah. So, what does this mean though? So we got our answer. What does that tell us? Really and truly, we don't care too much about these constants, but for the moment, we're supposed to focus on the constants. We were actually counting a specific thing. What was it? The number of basic operations that actually got executed. And so what that tells us is if you put in a value n for q, the number of basic operations that get executed is 3n plus 1. So if I want to understand what would happen if, for example, let's say I was timing this now, and suppose, as a crude assumption, that in fact it was true that in the hardware, every one of these operations took the same amount of time, it was 1 clock cycle, for example. And now I did a measurement and I saw that when I put in, n at say 1 billion, it took 1 millisecond. If I now went to 2 billion, how much time would I expect on that clock for that 2 billion size input to take? It took 1 millisecond to do the 1 billion. If I put in n equals 2 billion, how much time should I expect it to take? How much? You think it still takes 1 millisecond? Why are you guessing? You said possibly. Why do you think it wouldn't matter? What? 4 milliseconds? Is that a guess also? Or you actually worked that out? Somebody else said 2. Nobody wants to own the 2. But 2 is the right answer. Sorry? No, you want to own it. Why did you have to guess about that? Okay, let's see what this means. If I put in 1 billion, what this is telling me is that the number of basic operations I just performed was 3 billion on 1. So if I put in 2 billion, then I would have performed 6 billion on 1. So if 3 billion on 1 took 1 millisecond, how much time do you expect 6 billion on 1 to take? Roughly 2 milliseconds, right? Well, about double the time. Yes? Importantly, what we're seeing is that the running time, the amount of steps, the number of steps required, in this case is varying linearly with the input. Which means that as you scale up the inputs, you would expect the running time to scale up proportionately. And that is why we really care more about auto growth than the specific constant. Because essentially the information in this is telling me, find out that T of n is theta n, then what that says to me is that, if I double the size of the input, n, if I double n, T of n, which is the number of time taken or number of steps required, is going to double. Because it grows proportionately to n. Got that? Any questions? Okay, before I erase this, I'm just give these guys another look. Yes? Which is that? All of that. Okay, not all of it, but I'll try and do what's salient. After solving the recurrence, we got T of n is 3n plus 1. The takeaway from that is not the 3 and the 1. The essential piece is that it's theta n. Why is that the essential piece? Is that if we are actually measuring time, and we care about how much time, because about performance, right? So if we're really worried about how efficient our code is, we want to have a good way of predicting how much time it's going to take if we were to change the input size. So what I was illustrating to you is that if you double the value of n, T of n almost doubled. It went from 3 billion on 1 to 6 billion on 1. That's nearly double, right? And in fact, the bigger the n is, the closer it will look like to actually being double. So if doing 3 billion on 1 of these operations, and all of them take the same amount of time because it's one clock cycle, then doing 6 billion of them is going to take twice as much time. And so what I would expect is that as I double my input size, the amount of time needed is doubling. That's what this tells us. So knowing that T of n is theta n tells us that if you double n, this T of n is going to grow with n. So the n double and T of n doubles. And that's what we want to pay attention to. So the upshot was, it's not the detailed 3n plus 1 that matters so much. It's the order of growth at the end of the day that matters so much. And what we're trying to do when we compare our algorithms is not too much concerned with the specific exact number, but more with this order of growth. When we compare algorithms, we're going to look at the order of growth of it, of the algorithms in question, rather than the exact count of operation. Okay. So while we're on that topic, I'll save the ADT review for Friday because it's relatively straightforward. It's revision anyway. And since we're on this and you're all warm, let's do another example real quick. You won't be able to solve it, then leave the solution to when we have the more high-powered techniques. You can try on your own to solve it after. But let's see if we can at least get to the recurrence relation and begin to get a grasp of why it might be better. Do you remember? Oh. All right. Let's look at an alternative way to do this. Some of you were coming up to the board yesterday and asking, couldn't I do some doubling or some halving, something with the shift? It was kind of mumbled, but you're on the right track. I don't remember who it was. More than one person actually asked me about that. Let's try and derive an algorithm that perhaps has a chance of performing better than this. So you need to remember, mode 1, its performance is theta n. Let's look at an alternative algorithm for the same problem. We're trying to multiply P and Q, see if we can do it any faster. That's the question, right? It would be like one of your homework problem set challenges. You get an answer right, but it only works for the small values. And when the n get very big, it busts up, right? Don't run in time. And so the question is, how do I get this to go faster? All right, so let's look. In this case, suppose that I look at it a slightly different way. I could regard the product PQ, this is going to be method 2. All right, clearly if Q is 0, it's still 0. I could say though that if Q were even, then certainly P times Q is the same as 2P times half Q. Say yes. And I can get 2P in one or two ways with the hardware that I have. I give it the easy one. I could add P to itself. What's the other way I could do it? Not right shift, left shift. I can left shift by one place. Okay, so it makes sense then to contemplate this. I could say that this is 2P times Q over 2. And that's if Q is even. But if it's odd, I better not try to divide by 2 because I'll get an error, as in I'll get an error in my answer. So let me just stick to what I had before. From this, I can derive an algorithm. It looks like this. If Q is 0, return 0. How do I check if Q is even using the hardware that I had? Oh, I gave it even was a basic option. All right. Well, we discussed this yesterday, right? But I guess that's not legal Python. Q is even, what was that? We need to multiply. So what's this? How do I do this mode? What? Recursion. That's what you said? Oh, that's the, oh, you're talking about this one. I'm talking about this product. But all right. How do I do this product? This 2P times Q over 2. So this is where the faith comes in. You have to believe that this is going to work. So you're going to use the function you're trying to write to do this product there. So you're going to return mod 2 of, now the 2P, you can do the left shift or you can do P plus P, whichever you prefer. P plus P. That was quite forthright. All right. And then the Q over 2, that one, you don't really have a choice. Finally, else return P plus, and that product here is recursive call to mod 2 of P and Q minus 1. That make sense? So that name is actually, the name of that process is actually called repeated doubling. Okay, so repeated doubling is what we're using here. Now let's see if we can get the time complexity of mod 2. So remember, the beginning of any analysis starts with what? Identify basic operation. Well, it's the same hardware I assume we're working with, so this is not going to change. And in a way, we deliberately deliberately set up our basic ops to have not changed because we knew ahead of time we might be comparing it with another one. Next step, size of input. Okay, what are the inputs to this function in the first place? P and Q, right? Which of them is it? Either, it could be neither, both, or only one. Which of them contribute to how much time it takes? Both? Why both? How does P affect the time it takes? When you look at what, okay, how does this function stop running? It depends on what we're testing for. So when we look at this check, but this is one exit, you can return here, that's checking for Q. This one, you could exit here, and again, that's checking for Q. And then finally, so all these tests were on Q, and therefore Q is what controls when we're going to stop. Yes? So in a way, the value of P doesn't really matter unless you are taking into account the fact that maybe if P is very, very, very large, this plus is not constant time anymore. But in that case, plus wouldn't have been here as a basic op. So long as plus is a basic op, it doesn't really matter what its argument sizes are. The value of P doesn't really change how much time this takes, and therefore only Q matters. So look, just like in the previous case, the definition of our size of input would be the value of Q. So now we want to try and assess the time complexity. And what I'm going to do is do a little bit of forward looking. So again, I'm saving myself some writing here, and I encourage you to do the same. You see that just based on what happened last time, when we started that time complexity analysis, the analysis for time for mol 2, once we evaluate this if, is going to yield an evaluation of time for mol 2 again. So it's going to make a reference to itself. So rather than writing it out so many times, I'm just going to create that abbreviation from now. So I'm going to say let T of n, okay, since I already have T over, I'm going to call it T2. So that's just a shorthand. T2 of n is time complexity for mol 2 of P and n. Because we're saying the value of Q is n when we're talking about an input of size n. Now we want to understand what T2 of n looks like. So T2 of n is what? Remember, you need to simulate this. So if you were to call mol 2 with P and n, what would happen here? You're going to execute this equal. So there's 1 for the equal plus 0. The 0 is not because this number was zeros. But any number would still cost 0. Okay, if that didn't happen, then we'd fall through to the elif. And even is one of our basic ops. So that's going to have another cost. But notice that if in fact Q is n is even, to get here we would have had to evaluate that equal already. So we can't ignore it. So it costs 1 for the equal plus 1 for the invocation of even. That's just to do the test. And then if it's true, we're going to come through and do all these operations here. So that's going to be plus 1 for the right shift, plus 1 for the addition, plus the time for the recursive call, which is T2 of, now what size argument did it receive? What is the numerical value of a right shifted n? If you took the value n, right shifted it by 1 bit, you divide it by 2. So that's half n then, right? Yes? And then what's the final case? To get here, we still have to test equal, and even. So we can't leave those out. And then the call here would have involved, oops, pointing at the wrong thing, sorry. This one would have involved 1 for the minus, plus 1 for the addition, plus the recursive call. With what size argument? N minus 1. Simplifying. There.
I'm gonna.
Oh. There. Oh. I'm gonna say you come and have a seat. Yes, question. If you had a value n and you right shift it by 1 bit, what's the new value? Not sure? If you take 4 in binary 1, 0, 0, right shift it by 1, what you get? You don't know, right shift it. You get 1, 0, right? Or what's that numerically? 2. So in general, if you right shift by 1 bit, you're dividing by 2. All right, let's simplify. So T2 of n is 1, n equals 0. That's 1, 2, 3, 4. If n is even, and 1, 2, 3, 4. Plus T2 of n minus 1, otherwise. Yes? The question was, where I have Q right shift 1, could I not have put Q divided by 2? And that would be legal if you actually had a divide operation. But the premise was that the hardware doesn't support divide. So you can't invoke an operation you don't have, right? But the whole point of it, I don't know if you were there yesterday, but the point of it yesterday was that you're given some hardware that doesn't support operations that you need, like multiplication. But it supports things like shift by two, shift, which is divide and multiply by 2. And so we want to use those operations that are given to us to implement other operations that we need. Okay, so any ideas how to simplify this? Well, if you remember the discussion that I had with you on last week, Tuesday, in fact, and I kind of helped you sort of just work through how many times that other function was called. I think we're doing exponentiation. Was it exponentiation? I think so. And I said to you, you know, I think the example was input was like 256, and one of them was decreasing by 1 every time, and the other one was decreasing by halving each every time. And I showed you that if you kept halving 256, you don't need to go 8 times before you start. Whereas if you kept subtracting 1, you'd have to subtract 255 or 256 times before you terminate. So that was clearly a big difference in terms of the number of passes in that context. You can use a similar reasoning here. Although you have 3 cases, because they're interrelated, if n is odd, then n minus 1 is used. And now at this point, we can talk about what's called worst case analysis. So if I'm going to try and get this exact for n, it's going to be too complicated because I have these 3 cases to contend with. But what's the worst that could happen? which of these two options makes n decrease slower? N minus 1. So the worst possible case would be that I got a special kind of n that forced me to use the T2 of n minus 1 branch as many times as it possibly could. That would be the worst case, yes? But we have already recognized that actually it can't be as bad as it might have been imagined to be, because when n is odd, n minus 1 is even. So you can never take n minus 1 branch twice in a row. So then the worst case is actually that when your n is odd, and then n minus 1 becomes even, and then when you divide by 2, you get odd again. And then you subtract 1, you get even, and then after dividing by 2, you get odd again. That's how you get worst case, right? So in that case, what we could do is we're going to reduce these two into a 2-case situation rather than a 3-case situation. Because in that case, we could say, well, I'll just treat it as if I had to take 2 steps at a time to see what that n would reduce by. In other words, when I'm going from one odd case to the next odd case, it's really 2 steps. It's odd, then even, then odd again. And that would be the worst case. And in that case, I can then combine these two. And so in that case, I can then write this. And so that T2 of n would then be 1 if n were 0. But in worst case, it's 4 plus T2 of n minus 1. And then that T2 of n minus 1 when n is now even, so n originally n was odd. The T2 of n minus 1 when n is even will now be this branch. So that's another 4 plus, now we have to be careful, it's T2 of the new value of n is actually n minus 1. And that's special to the worst case, which is what we're trying to analyze. In other words, everything else can be worse than this. So we get a handle on this, we will have a bound on the performance. Now this is something that we can analyze. You have seen from this maths, you could solve this. In this case, we get a plus T2 of n minus 1 over 2. The techniques for solving this, we will discuss in great detail, so we don't need to get into this right now. But hopefully what you can see from this is that this is going to be significantly quicker than the other solution. If you just put in, try as an example, as I said, like 256, 456 another one, like by 1 each time. 256, well, this is odd, worst case. 255. 255 would have been 254. So 255 would lead to 127. 54 over 2. 127 would lead to 127 minus 1, 126 over 2, 63. 63 would lead to 31. 31 would lead to 15, 15 to 7, 7 to 3, 3 to 1, and then finally to 0 when you're done. So you'd have solved that in about 8 iterations of this process. Each time you'd have incurred an overhead of 8. 8 is 64 or so. So in total, maybe you'd have spent about 65 operations or thereabouts calculating that. Big difference between, so remember, 256 was the input side. When we actually have the techniques for this, we'll revisit this and get the function, you'll be able to compare them. But for now, I hope you get a glimpse of how much more powerful or faster, how much more efficient this algorithm is than the other one. Same problem, different solutions, one is way superior. All right? See you on Friday.
Are you the